This is May-June 2024, paper 42. This is May-June 2024, paper 42. In this paper, I've written down the definitions of theoretical answers for your convenience so that you can pause the video and read the answers. I will be discussing them, but I've written them in clear English so that you can understand how to write the answers for yourself. So the first question is about defining the radian, that is the angle subtended at the center. So the angle will be called as 1 radian if the arc length, which is this one, if this arc length S is equal to r, the radius of the circle, then that theta will be called as 1 radian. And no matter what the size of the circle is, 1 radian is generally equal to 57.3 degrees. Okay. Moving on to the next question, he says the circular metal disc is so and so spinning horizontally like this, and the total radius is given to us as 9.3, and there is a piece of clay at the edge, or 1.2 centimeters from the edge. So the distance from the center up to this point will come out as 8.1 centimeters if you subtract 9.3 with 1.2. He says for this part, an arrow labeled V showing the direction of velocity. Now we need to see in which direction this rotation is taking place. So if it was rotating like this, then the velocity would be coming like this. But since it's rotating like this, then the component of the vector component of velocity will actually be like this, making an angle of 90 degrees with the center. Then he says label an arrow A for the acceleration. Acceleration is always towards the center of the circle in the direction of the resultant force. So this will be A. Next we have a question. He says calculate the angular speed. So we have a certain tangential velocity, which is V, and the distance from the clay. But we can't use this 1.2. We have to use the distance that is from the center, because that will be the radius r, or the distance r from the center of the circle to that specific point. So this is going to become, first, that is for the disk. So this will be V equals to r omega, right? And we have the speed of the clay is 0.68. R will be 8.1 into 10 raised to the power minus 2, and omega is what we are looking for. So omega comes out as 8.39 radians per second. So this will be 8.4 up to 2 significant figures, right? And as long as the disk is same, as long as everything else is same, omega usually in these questions is considered to be a constant entity as long as the RPM is exactly the same. Then he asks you calculate the acceleration A from the center of the gravity of the modeling clay. So we have multiple formulas for this. We have A equals to r omega square, and we also have V square over r. So no matter what formula you choose, the answer will still be the same. So I'm choosing V square over r. So this is why I'm choosing V square over r, because it's possible that in the previous part, if I made the error in omega, I'm still sure about the value of velocity V. So owing to this guarantee, I'm preferring to choose this formula. So then we have a 0.68 whole square divided by 8.1 into 10 raised to the power minus 2, because it's centimeters. So A comes out as 5.708 meters per second square, which will be 5.7. In the next question, he said there is a second piece of modeling clay. The first one and second one. Second one is placed a bit closer. This is your second one, and this is your first one. The second piece of the modeling clay, okay, is placed. By placing one tick in each row, complete the table showing that how this quantity is indicated comparing between the two pieces. How will they be amongst each other? Now, angular speed, as I discussed earlier, will remain the same for both of them. Omega remains same, because in this entity, or in this equation, which is V equals to r omega, the relationship is primarily between V and r. That as long as you're going away from the center, your tangential velocity will increase, but the omega, if they exist on the same disk, will remain the same. So the angular speed is supposed to be the same for both of them. Then he talks about the linear speed that will be less than the first piece. Why? Because as we can see that the second piece is much closer in terms of the radius, or in terms of from the center. Now we have developed this proportionality that V is proportional to R. So if R is low, then V will also be low. That's why the linear speed is less. And in terms of acceleration, acceleration will also be less than that, because acceleration, again, that is proportional to V square over R. Now if you want to compare this with acceleration being proportional to omega square R, or r omega square, then that relationship will not be justified in terms of omega, because omega is constant, and that will be justified in terms of R, because if R is less, acceleration is less. And over here, since due to the reason that R is less, V is less. So if V is less, acceleration will also be less. So no matter what logic you use, these will be your answers, right? But always prefer to use mathematics, or try to argue with these situations in terms of mathematics. Don't just guesswork for these questions. Again, question number 2, it says, with reference to thermal energy state, what is meant by thermal equilibrium? So thermal equilibrium state, so it means that any objects that are supposed to be, or that are referred to as being in thermal equilibrium, their thermodynamic temperature is assumed to be constant, or assumed to be same, so that no more further exchange of energy is taking place. Now, let me give you an example from the daily life. If you bring a cup of coffee that is, let's say, at a high temperature, let's say at 70 degrees centigrade in your room. Now the coffee is at 70 degrees centigrade. Your room is at a pleasant temperature of 25 degrees centigrade. If you leave the cup of coffee or hot water in your room for a very long amount of time, you will realize that this comes down to, or cools down to, 25 degrees centigrade. There needs to be a temperature difference for thermal energy to be exchanged between two systems. Now, the energy exchange will happen as long as there is a difference. And when the temperature or thermodynamic temperature of both entities, the room and the cup, become equal, that situation, in that condition, we will say that these two things are in thermal equilibrium. So although this feels like an intuition case, this feels like something that we already understand and know, but we have to state this in order for questions or calculations to be made, or some assumptions to be made. In the next part, he says that there are two cylinders with the respective values given to you in the question, right? He says, state the temperature of gas X. Now, we will use the thermodynamic equation, which is PV equals to nRT, and we just have to plug the values. So pressure is given to us as 1.2 into 10 raised to power 5. Volume is 0.0260 by the unit meter cube. So N is the number of moles, which is 0.74 given over here, right? And R is the universal gas constant as 8.31. You can check this in the data cable as well, data booklet as well. So this will be temperature plus 234, right? Because we are looking for the thermodynamic temperature. So, sorry, this will be 273, an addition of 273. Because if you have to convert degree centigrade into Kelvin, you have to add that number, right? So eventually, this number becomes, when you calculate this, the value of T comes out, because we have to show that this is 234, right? So when you calculate this, your answer is going to come out as 234 degrees centigrade, right? Okay. So the next part, he says, determine the value of N, the number of molecules of the gas, and explain your reasoning. When he says explain your reasoning, please write down a statement. Please say something, but why are you using these values, or why are you using that value, X, Y, Z, so and so. Now, we see that in this question, he says that the samples are in thermal equilibrium. If they are in thermal equilibrium, that means whatever the temperature of X is going to be, Y is going to have the same temperature, right? That's why we call this a thermal equilibrium situation. So you will say that since they are in thermal equilibrium, write down full words, I'm just cutting it short. They have the same temperature. They have same temperature. Hence, T is equal to 273, oh sorry, yes, 273 plus 234 equals 507 point, sorry, you can take this 507 kelvins, right? Then you reuse the equation PV equals to nRT, that is your choice. Either use PV equals to nRT, or you can use PV equals to capital NKT. That's your choice. Both options will give you the same answer. But the first one, this formula will call you for another extra step, because we want to find the number of molecules. This step gives you only the number of moles. So again, let's plug in the values. We have 2.9 into 10 raised to power 5. Volume is 0.043 equals to N into 8.31, and temperature is 507 Kelvin. So over here, the number of moles comes out as 2.957, then multiplied by Avogadro's constant, which is 6.02 into 10 raised to power 23. So the number of atoms or molecules comes out as 1.78 into 10 raised to power 24 atoms, molecules, whatever you like to call it. If you use the second method, then again, plugging in the values gives you 2.9 into 10 raised to power 5. Volume is 0.043. Now equals to N is the number of atoms now. This is already multiplied with the Avogadro's number. That's why we don't know what this capital N is going to be. So K is Boltzmann constant, which has a value of 1.38 into 10 raised to power minus 23. And the temperature is 507 Kelvin. So in this, you get the number of atoms straightforward directly, which is again 1.78 into 10 to the power 24. Now, rounding this off to two significant figures, so the final answer is going to come out as 1.8 into 10 to the power 24 atoms or molecules. This is what you're going to write down over here. I've shown you both methods. Whatever you're comfortable with, that is fine. Question number 3 says that the gas X contains molecules that give X has a mass of 4 times X, and the gas Y has mass only 1 time, right? So what's the difference between the speeds? I will explain the theory to you first, explain the theory to you later, but first look at the proof of this. Now, since the system is in thermal equilibrium, right, as opposed to given in the previous information, so the thermodynamic equation is 1/2 mv square, or half mc RMS square, equals to 3/2 kT. Now, since they're in thermal equilibrium, this 3/2 kT is going to be exactly the same for both gases, be that for X and be that for Y. So half mv square for Y, they're going to get the same answers, right? So it only comes down to the comparison of half mv square with a half mv square. So let's compare them. So for X ratio Y, we have 1/2 mv square compared with half mv square. So we're supposed to compare the velocities with reference to masses. So half gets cancelled out, and the mass of X is 4 times mass into Vx whole square equals to mass into Vy whole square, right? So m cancels out. You take m over there. Sorry, this m is cancelled out, so it can stay over here. So we are left with 4 equals to Vy square divided by Vx square. Taking the under root on both sides, we are left with 2 equals to Vy, and you take that Vx over there, so this becomes 2Vx equals to this. So this is what you're going to write down, that the speed of X is half the speed of Y, or the speed of X is double the speed of Y, whichever way you choose to write this down. So this was the proof, and this is the mathematical or the English that you can write down to explain this to the examiner, right? So it says that since the system is in thermal equilibrium, the molecules have the same kinetic energy. So you have to mention this first point, that why are you going to say what you're going to say? So we have told the examiner that they are exactly the same temperature, but that is why I'm going to compare half mv square with half mv square of both molecules. According to the thermodynamic equation, half mv square equals to 3/2 kT. All variables are constant, and hence we are only left with this equation, which is going to be V proportional to under root m, because V was square taking under root on this side. This is what the equation looks like now. And then RMS speed, and then you give your conclusion, because of course you have made this proof in your head. You can use this space to write down the proof as well. So RMS speed of molecules of X is half the RMS speed of Y. You can also say the same statement in terms of doubling the speed of Y in favor or in reference to X, right? So it doesn't matter if you write it down like this or you write it down like this, Vx equals to 1/2 Vy. I've mentioned it in this way. You can mention it in this way as well. Does not matter. Question number 3 is from first law of thermodynamics, temperature chapter, right? So it says what's meant by internal energy. Again, a common definition: the sum of randomly distributed kinetic energy and potential energy of the system of all the molecular system represents the internal energy of the system. So the equation actually looks like this: the internal energy is equal to sum of kinetic energy plus sum of potential energies. And to put it in plain perspective, just a short summary: the internal is equal to kinetic plus potential energy. Kinetic comes from temperature, it comes from heat. Potential comes from the number of bonds, or you can say the distance between the atoms or distance between the molecules, right? Because if you bring them close together, if you increase the pressure, then they come close to each other and bonds can form again, right? So that is why it is discussed in terms of bonds and sometimes in terms of distance. It represents the same distance, same thing. So that P delta V actually comes from this, right? Okay. So first system, he says, explained in reference to the first law of thermodynamics, that a gas is heated at constant volume. If the volume is constant, remember, then the potential energy is 0, or the change in potential energy is 0, because P delta V is 0. Delta V becomes 0, the pressure is not 0, so the whole multiplication becomes 0. So we have to state this, we have to discuss this and tell the examiner that why am I saying that whatever I'm trying to explain. So since the volume is fixed, the molecular distance is constant, hence the potential energy is also constant, or is not going to change. Now, since this is the case, because the equation is kinetic energy, plus potential energy, if this is zero or the change is zero, then the only equation we are left with is internal energy being dependent on the kinetic energy. So that is where we draw the conclusion. Temperature is proportional to kinetic energy. Again, stating this information is important. Since temperature is being increased, since you are increasing the temperature, the kinetic energy also increases. Since kinetic energy increases, the internal energy is also going to increase. So that is why we conclude, that is how we conclude that leading to an increase in internal energy. Now, same logic is for part number 2 as well. A wire is stretched with an elastic limit at a constant temperature. Now, notice if the temperature is constant, and we know that the kinetic energy is proportional to the temperature. If temperature is not changing, kinetic energy is not changing. Again, simply put, if internal energy is equal to kinetic energy plus potential energy, then kinetic energy is not participating. So we are left with internal energy being only proportional to the potential energy. Now, in this situation, what is the source of that potential energy? Where is that coming from? So since this is a thin wire or a spring or a rubber band being stretched, so the potential energy is primarily elastic potential energy because of the rearrangement of the molecules as they slide over each other when you stretch them. So again, stating that this temperature is constant, this means the kinetic energy is constant and does not contribute to the internal energy, which is what we stated over here, that it is going to be eliminated from the equation. The elastic potential energy is proportional to the square root of extension. We know this because in A levels we've done this formula, that half kx square is a formula for elastic potential energy, and elastic potential energy is proportional to x squared. So we have to state this information as well. So energy is proportional to the square of extension, hence the potential energy increases, and if that increases, simply put, if potential energy increases, elastic internal energy also increases, causing an increase in internal energy, right? So I hope that we understand this question and how to answer this question and how to get 3 marks for this. All right, question number 4 is a simple harmonic motion. Just by looking at the question, we can figure that out, that there will be some oscillation. There is a graph of acceleration and displacement given to you. And this is also a very common question. Students who have done this question from the past papers realize that the characteristics of this graph are asked many times. In the recent past papers, he did not, but I was expecting that this question is going to appear in this question or in this paper because he hadn't asked about this acceleration displacement question from a very long time. So what are the characteristics of this graph that show that this is a simple harmonic motion? What are those characteristics? So the first characteristic is going to be the negative gradient, right? But let's start with a simple one. So the line is passing from the origin. This means that this is simple harmonic motion. Plus, it's a straight line. It's a straight line passing from the origin. It has a negative gradient, which means that acceleration is inversely proportional or is opposite to the displacement, right? And we can also say that the gradient represents the omega or the angular velocity, right? Now let's observe this graph. Let's do a quick review. You see, for the case of a pendulum, let's say that this is the mean position, and moving to the right side is a positive displacement and moving to the left is a negative displacement. So there are only 2 situations in which this pendulum is going to exist, either on the left, either on the right. When it goes to the right side, the weight component tries to bring it back to the mean position, and when it goes to the left side, the weight component tries to bring it back or tries to move it to the right side to bring it back to the central mean position. Now we can observe over here that when the displacement is positive, the decelerating force or the accelerating force is towards the left, which is negative. That is why you see that when the displacement is positive, when the displacement is in the positive region, your accelerations are in negative region. And similarly, when it goes to the left side, although the displacements are negative, the acceleration becomes positive because now it is trying to move towards the right side, which is the positive direction, right? So this is how we observe this graph, right? All right. The next parts are purely mathematical. So please bear with me. I will be explaining the mathematics as well, so just hold on. So he says, derive an expression in terms of m, a, and y. In terms of, we have to represent a or use a, y, and m to represent these equations. So we know that omega is equal to, or acceleration is equal to omega square x or omega square x naught. Let's replace all these values from the graph or from the situation. That is going to be a equals to omega square, and the displacement is actually being represented as y. So if I write this down over here, then this becomes omega square a divided by y, Then taking the under root over there, this becomes omega equals to under root a divided by y. Now, if we go back to the graph, we realize that we have some values mentioned over here. So the extreme situation over here is 3y with an amplitude of 2a. So let's mention those things over here as well. So this will be omega equals to under root, amplitude was 2a, and the acceleration is 2a, and the amplitude y is actually 3y. So the formula becomes whole under root 2a divided by 3y. This is what omega is equal to. Similarly, in the next part, he says find the maximum velocity. Now we understand that for the velocity formula, which we have, v is equal to omega under root x naught square minus x square. Now for the maximum velocity, we understand that the the displacement vector from the mean position has to become 0. Or you can say that the system, the pendulum or the oscillation has to come back to the central position. At this point, the x is equal to 0. And the displacement, which is always the maximum point, x naught, is not equal to 0. And in this situation, if you want to compare this, let's say we use this situation. So the block oscillates between two positions. Let's say that the initial position of the block is this one, and the final position of the block is this one. And the central is the equilibrium position. Okay, fine. So where are these variables going to exist? So the maximum displacement, either up or down, is referred as x naught. Either this one or either this one. This will be x naught in that equation of velocity. The x actually comes from the current position. Where is it now? Let's say that the block exists at this position. So from the mean position to this position, this will be the value of x. So if we write down the formula of velocity again, omega under root x naught square minus x square, this x is actually this variable. And the maximum displacement is actually this variable, right? So if I want to look for the maximum velocity, it can only happen at the mean position, because at only that point, the pendulum or this oscillating mass is moving at the highest speed, because there is no decelerating force component trying to stop it or trying to bring it back to the mean position, right? So that is why this equation for maximum speed only comes down to, now since this is an under root of x square, so this becomes x only. And we understand that this is going to become 0 because the maximum speed can only exist at the mean position. So x becomes 0. So keeping this in mind, we have this equation. So the maximum Vmax velocity equation becomes omega x naught, right? Now we have the formula for omega in the previous part, and we understand that the x naught or the amplitude is actually 3y, right? So let's replace all those values. So we have under root 2a divided by 3y. This is being multiplied by 3y, right? Now, it's all a matter of mathematics now. Let's separate the variables. So we have under root 2a divided by under root 3y multiplied by 3y. So if we do the mathematics power rule, I'm sure that you can do this with a simpler method as well, but I'm breaking down for those who don't understand this. So let's deal with 3y and 3y. So we have 2a raised to power 1 over 2. And multiplied by with 3y raised to power 1 minus 1 over 2. If you bring this over to the numerator, then you have to subtract the powers. I hope that we understand this rule from mathematics. So we come down to this idea. You can do this by conjugate method as well. If you're familiar with that, that is also fine, that's acceptable. So this becomes under root 2a multiplied by under root 3y. So combined, this becomes under root 6ay. So the answer will be 6a capital Y. Okay. Question number 3. So the energy E of the oscillation. So the formula is half m v square, and we understand that the velocity is half m. Then we have omega square, and then we have the x naught square. Now, since it's the energy of the oscillation, so we will be finding the maximum energy or the total energy of the oscillation. That's why we will be taking the maximum velocity component, right? So let's replace the values. Half into m into, if you take the square of this, the under root goes away. So that will be 2a divided by 3y into, again, x square. If you take the square of the amplitude, this becomes 3y whole square, right? Then it's just a matter of algebra. You come down to the equation that is going to be 3a ym. So it could be 3ym, 3a-ym, 3m-ya. Does not matter what orientation you write this down. This is what your answer is going to look like. Okay. All right. Part C, he says write down an equation in terms of t, x, and t in seconds for x. Right. So I suspect that this is the equation that he's looking for. Xt equals to x naught either sine omega t or cos omega t, right? So we understand that x naught is actually the amplitude, which is what he has given us. That 3y is 1.8. So the first variable is pretty easy to figure out. So this will be 1.8 into sine of omega t. Now we understand that omega is equal to 2 pi f or 2 pi by t. So can we figure this out? Can we find it? Yes, we can, because the period of the oscillation is given to us as 0.75, right? So let's replace this value into this. So 2 pi divided by 0.75 gives me a value of 8.37. So this is 8.37 radians per second. Now let's replace this in terms of omega in this equation. So we are left with x of t equals to 1.8 sine of 8.4 t, but this will be in centimeters. Why? Because the whole system or the whole function is for the displacement at the time t of my choice. I put t of my choice. This equation gives me the displacement at that exact instant. So I will write this down as 1.8 into sine of 8.4 t, and I will mention centimeters. Okay. All right. Question number 5 says electric potential, very old and very repeated definition. Work done in bringing the unit positive charge from infinity to that point is called electric potential. And the formula for electric potential V is equal to Q divided by 4 pi epsilon naught R. I'm sure we're familiar with that. So it says there are two isolated spheres of different sizes. They are placed in vacuum, which means that there is no one else other than them. Their centers are separated 1.2 meters apart. And there is a line joining them, which is XY, which is this line. And that point P exists on that line. Okay. The genetic statements that we find in previous past papers as well. So it says figure 5.2 shows what's what and the potential of two spheres. Okay, fine. He says state three conclusions which may be drawn about the spheres. So I've color coded all the discussions I'm going to do right now. So the first point is, the first observation that we do is that the radiuses are different, or radii are different. So sphere X, which is placed on the left, we can notice that its radius is 0.3, and the sphere Y, its radius is from this point to this point is 0.1. So we can write this down in two ways. We can either say the radius of X is 0.3 and Y is 0.1, or we can say radius of X is 3 times more than the radius of Y. Or you can say it is 3 times the radius of Y. Okay. And if we visualize the spheres themselves, then this is what the spheres look like in real life. Over here and over here. Of course, the rest of the sphere is over here, and the rest of them is over here. Okay. All right. So we've discussed about the first point. Let's discuss about the second point. The second point goes in terms of sphere X and Y have the same charge. They're both positive since their potential values are positive. You can see from the graph that this is a positive value. This is also a positive value. Since both have the value of potential to be positive, they are exactly the same. They have the same charge. They have the same sign of charge. But what can we say about the magnitude of charge that they both possess? Do they have the same charge or do they have different charges? This is what the discussion is going to be about the next part. So in this part, we discuss that they have the same sign of charge, right? They both have the positive charge. But in terms of the magnitude, what are the values of charges? Are they same or are they different? So we say that they have V min is at the midpoint line joint, which means that the magnitude of charge, is the same. They have the same charge. Let's discuss this point. You see, the formula for potential is V equals to Q divided by 4 pi epsilon naught R. Now, since epsilon naught and 4 pi are a constant, we can say that potential is being equal or proportional to Q divided by R. Okay. Now, if we move away in terms of R, the potential decreases or increases respectively. Let's discuss about the point which is exactly the same for both of them. It could be same for both of them. You could choose any point. So from the center of the sphere 1 or sphere X, is this X? Yes, this is side X and this is side Y. If we consider the distance from center of X up to this point, this is the potential. Let's call this Vx. And if we take the same distance from the center of Y, let's say move from this point and we move 0.3. We move 0.3 centimeters away at this location. So we are exactly at the same point. For X, we are at its surface, but for Y, we are exactly at this point, which is, of course, 3 times R of this one, right? We notice that the potential is exactly the same. How? Read the graph at this point, and you will see that the potential comes out exactly the same. So, putting in the value of R, 0.3, for both of them, for X and for Y, has led to the same value of potential, which means that the value of Q must have been same on both of them. They both have the same magnitude of charge, right? And the story doesn't end here. You can move ahead and retest this theory at another location as well. So let's try this again. Let's try this for another point outside the spheres, right? Let's move at a distance of 0.4 from the center of sphere X, come to 0.4. This will be the point of the potential for X. Let's try the same thing for Y. If we move in 0.4, let's say this is 0.2, again this is 0.4. We realize that the point of potential is again the same. So putting in the same value of R, giving the same value of V means that the charge is same. That's why we've concluded that the magnitude of charge is same. From this conclusion, we have said that the minimum potential exists at the midpoint. If they had different charges, then the potential would be different at the midpoint, right? Okay. All right. So he says that a proton is held at rest in the line joining. Okay, fine. He says that the proton is held at 0.6. So exactly the center, we have a positive charge. We understand that these are also positive charges as concluded in the previous part, right? And we also know that the charge or the value of charge, let's say if this is 50 nanocoulombs, this is also 50 nanocoulombs. Okay, fine. They have the same charges. Now he says what's going to happen. The proton is released, describe or explain with calculation, without calculation, what's going to happen to the motion of the proton. So since X and Y have the same charges, right? Proton is also positive. The proton will experience a repulsion from both sides. Naturally, if the proton is placed at the center, the positive charges repel. This force is coming from X. And from the left, we are going to experience a force due to Y on the charge in this direction. So this is force due to Y. And F will be equal to the Q divided by 4 pi epsilon naught R square. So since the number of charges, or since the charge on both spheres is equal, in reference to proton, the forces are going to come out as equal, because this will be 50 nanocoulombs, this will be the charge of proton for X and for Y. This R is exactly the same from both sides, which is 0.6, right? So the answer for force Y and force X in terms of magnitude will be exactly the same. So that is why we have said that the forces from both sides cancel each other out, because their values are same and they're opposite to each other. There is no resultant force, hence there is no acceleration. So the proton is going to be held stationary on its own position, even if you leave it to move, or even if you allow it or give it the liberty to move. It will not be moving. It will not experience any resultant force. Next question is question number 6 from capacitors, chapter of capacitors. I have explained this previously as well, that please practice the proofs, practice the capacitor proofs. He's going to ask you, and this is one of those questions. He says the capacitors of X is Cx and Y is Cy. He says find the expression in terms of the total capacitance and explain your reasoning. He didn't used to ask this question before as frequently, but now he's asking this because students just write down or jot down the proof that they've memorized. You have to explain why you're doing what you're doing. So the first statement you make is that the voltage divides. It's a series combination, so the voltage divides. Now, since the voltage has been divided, we can say that the voltage of battery is equal to Vx plus Vy. And from, then explain that from equation Q equals to Cv, we have V equals to Q divided by C, right? Okay, this is the next explanation that you've given. Then, they also underline this. Then you talk about, and then you say that replace, let's name this equation as equation 1 and this as equation 2. Then you say replace equation number 2 with equation number 1, and if you do that, what do you get? We get Q divided by C equals to Q of X divided by C of X plus Q of Y divided by C of Y. Then you make a statement again. How do you deal with this Q? Right? So you will have to say that charge on both capacitors is the same. And for series combination, why is that so? Because even if they're linked in a series combination, let's say that 100 electrons leave the battery and charge X. So 100 electrons have gathered on the left plate. 100 electrons will leave the other plate because of the repulsion, right? And they travel through the wire. And accumulate on the left plate. So 100 electrons accumulated on X. It caused the repulsion of 100 electrons from the opposite plate, and they also accumulated on the left plate of Y. So this is also 100 electrons. And then those electrons are going to be repelled and they go back to the battery. That is how the capacitors are being charged. So no matter the size of the capacitors, the charges in series combination remain the same. So that is why we say that the charge on both capacitors is same. Hence we cancel out the charges because the Q total of the battery is equal to Qx is equal to Qy. So we are left with 1 over Ct, the total capacitance, equals to 1 over Cx plus 1 over Cy. That's why in capacitors, when connected in series, follow this formula for total capacitance. The question changes entirely. He says capacitor P and Q are connected in parallel to each other, or the parallel power supply of voltage V. Capacitor of P is 200. Let's draw the circuit to visualize it better. So we have a capacitor P, which is 200 microfarads, and we have a capacitor Q, which can be varied from 0 to 400. So it's a variable capacitor Q 0 to 400 microfarads. He says that when Q is not a part of the circuit, when Q is 0, the total energy stored in the capacitor is 2.5. Okay, fine. So capacitor P will be the only element storing that energy. So we have the formula for E equals to half Cv square, right? So the energy is 2.5 into 10 raised to power minus 3 equals to 1 over 2. Capacitance is 200 microfarads, so 2 power minus 6 into V square. So V, after taking the under root, comes out as 5.0 volts, and then we will say that it is shown successfully. Okay. All right, moving on to the next. So the battery voltage is 5 volts. This is what was given from the battery. He says calculate the total energy in millijoules stored in capacitor CQ if it has its maximum value. If it goes to 400 microfarad again, what will be the case in that situation? Now we understand that the battery is still 5 volts. It is today still 5 volt. This is P at 200 microfarad, and this is now Q at 400 microfarad because we have increased its capacitance, right? So it is simply a matter of, you can do it two ways. You can use half Cv squared for this and half Cv squared for this and then add them together, or you can find out the total capacitance. So the total capacitance, since they are in parallel to each other, they will be added together. So this is 200 plus 400 equals to 600 microfarad system at a voltage of 5 volts. How much energy does it possess? So 1 over 2 into 600 into 10 raised to power minus 6 and 5 square. So this comes out as 7.5 millijoules. You could have also looked at it from a ratio perspective, that if 200 millijoules or 200 microfarad is only holding on to 2.5 millijoules, then if this capacitor is twice of the 200 microfarad, then this will be holding twice as much energy. So this will be 5 millijoules. So the total energy system would have been 2.5 plus 5, which again comes down to 7.5. So this is 7.5 millijoules of energy. In the next part, he says that we have 6.2, sketch the total energy stored in capacitors with CQ and CQ varied from 0 to 400. So we understand that we have to draw the graph with reference to CQ, but first let's try to draw a graph for another capacitor. We have a capacitor P of 200. So its value is not changing. So it possesses a constant energy of 2.5 millijoules. This will be for the capacitor CP. And we understand that the value of the Q capacitor, which is going to be varied from 0 to 400, if its capacitance is 0, its energy will be 0. If its capacitance is 400, as opposed to, or as figured out previously, it can store 5 millijoules of energy. So it goes up to 5 millijoules. So this alone would have been the graph of capacitor CQ. But since we're supposed to find out the total energy or the graph of the total system, we have to combine both of these graphs. Now notice how we do that. You see, when the capacitor CQ is at 0, capacitor CP still exists. So in the worst possible scenario, this is my starting point when CQ is not a part of the system. Now when CQ becomes a part of the system at the maximum value, it adds on top of this, it adds 5 millijoules of energy, right? So my ending point will be this coordinate. So this line, the red line, is just shifted upwards with a displacement of 2.5 millijoules. So this will be your final answer. The rest of the lines were just drawn for discussion if this question had been asked in terms of a different scenario. So this will be your final answer, right? So this energy is contributed by P and this energy is contributed by Q. Moving on to the next part, question number 7, he says, again, a repeated question, law of electromagnetic induction. Magnitude of induced EMF is proportional to the rate of change of magnetic flux. The word linkage is in brackets. You can add this or you can omit this, does not matter. So the equation actually looks like that the induced EMF is equal to rate of change of magnetic flux with respect to time multiplied by the number of turns or the number of turns of the coil. He shows a magnetic field in a coil with a voltmeter attached. This is our magnetic field that is changing. It's a good sign. If the magnetic field is changing, then an EMF will be induced. Now he says that the coil has 340 turns. This is the area. He says maximum magnetic flux through one area. And the formula for magnetic flux is phi equals to BA. If he had asked me about the whole coil, then I would have multiplied the number of turns N as well. But it's not required over here because he's asking me for one coil. So the magnetic field at this point, let's choose the maximum magnetic field. That is this point, which is going to be 7.2 millitesla. Please count the number of boxes yourself. So that is minus 3 into cross-sectional area, which is 3.2 minus 4. So the phi, or the magnetic flux density, or the magnetic flux itself we're getting is 2.304 into 10 raised to the power minus 6 Webers, right? So this will be 2.3 into 10 raised to the power minus 6 Webers through just one coil. The next part, it says determine the maximum rate of change of magnetic flux. Now notice that this question indirectly is asking you about the induced EMF, because only then we have the induced EMF with the magnetic flux linkage. The rate of change of magnetic flux represents induced EMF. So this question is about induced EMF, right? So don't be confused by that. Now let's figure out all the values for this question. So first let's write down the formula. So the rate of change of magnetic flux will be EMF being equal to rate of change of flux divided by time multiplied by the number of turns, which will become AN multiplied by change in the magnetic field divided by change in time. So we have the cross-section area as 3.2 into 10 raised to the power minus 4. We have the number of turns as 340, but we need to find out the rate of change of magnetic flux as the gradient from the graph. So we go back to this graph and we draw a tangent, right? So you can either draw the tangent at this point or at this point, it's your choice. I have selected a positive gradient, so I draw a tangent at this point, then choose two coordinates over here, mention those coordinates over to the graph, over to your solving procedure. Please show the tangent line and the coordinates that you've selected over here. So the coordinates from the graph that I have selected, yours can be different, it does not matter, it's okay, it's fine, come out as 7.8 millitesla, comma, at a time frame of 2.9, and the other coordinate that I selected is 2.0, comma, 1.2 millitesla. So just write this down as a change or the gradient itself. So this becomes 7.8 minus 1.2, and it is understood that I have added the 10 raised to the power minus 3 with all of them. I don't have a writing space over there, that's why I'm not mentioning it. Divided by 2.9 minus 2.0. Once you've finally done that, once you finally calculate everything, this answer comes out as 0.797 into 10 raised to the power minus 3 Webers per second. This is voltage. This is actually volts. So this is 0.80 into 10 raised to the power minus 3. That is why he says state the maximum, because now the answer is going to be very simple. That is 0.8, exactly the answer that we got before. Okay. All right. Then we have this graph. He says sketch for EMF V across the coil from T0 to T6. Now I'm going to explain this question. I have redrawn the question over here because it requires the diagram of magnetic flux, magnetic field, and the voltage simultaneously. Now first we need to understand the Faraday's law. That is EMF is proportional to rate of change of magnetic flux divided by time. And if we add Lenz's law in this, there will be a negative sign in the situation, which means that this, which represents the gradient, if the gradient is positive, positive multiplied by negative gives me an answer of negative EMF. And if the gradient is negative, then negative multiplied by negative of the Lenz's law gives me a positive answer for the EMF. So first, I would recommend figure out the gradients. So over here, we have a positive gradient. This is negative. This line is positive. This line is negative. This is positive. And this is negative gradient. So once we figured out the gradients, we can figure out what voltages we're going to get at those specific points. Do we have a gradient or do we have a slope at these locations? No, there is no rate of change at these points when the gradient does not exist. So at these locations, the voltages will be zero. So let's mark those points. So 0 voltage, 0 voltage, 0 voltage, 0, 0, 0, and 0. No gradients, that's why 0 voltage. Now let's go back to the gradients. So in the first section, we have a positive gradient. If the gradient is positive, right? If the gradient is positive, the voltage should be negative, because in terms of this, the positive multiplied by Lenz's law gives you a negative answer overall, right? So there should be a negative maximum EMF over here. When the gradient is negative, the EMF is supposed to be maximum positive. So similarly, following the same idea, we draw these coordinates in these locations. So when the gradient is negative, we have the maximum induced EMF, but opposite sign due to the Lenz's law, right? So now we just have to draw, it's a matter of just drawing the graph through the points. So it's going to be like this. Try to make it as smooth as possible. Like this. So I'm not going to draw this graph again in the previous question, but this is how it's going to go. This is how we visualize it. Okay. All right. So I've already drawn this question in the next page, so I'm not doing this again. He says the variation V of t can be represented as this way. We have done this in simple harmonic motion as well. So it says give me an equation where A and B are constant, determine the value of A and B, give units for your answers. No problem. So we have found that the maximum, absolute maximum EMF V naught is going to be 0.8. So if we write down this V as V naught sine omega t and compare this with what the examiner has given us as sine bt, then A is basically the maximum amplitude, which is going to be 0.80 into 10 raised to the power minus 3 volts, right? And the B is actually the omega, and omega is equal to 2 pi by t. I can use F as well, but the graph is in terms of time, so let's use time for that. So for that, we can calculate the time for one oscillation or one complete period. We can see that from this point to this point, this is one complete oscillation, or you can choose from this point to this point, this will be one complete oscillation, or you can also choose from the starting point to the ending point when they both become or reach the mean position. But I prefer crest to crest and trough to trough. It's easier to see. So that is 2 milliseconds of time. So this becomes 2 pi divided by 2 into 10 raised to the power minus 3. So omega comes out as 3141 radians per second. Up to 2 significant figures, this will become 3100 with a unit of radians per second. So this equation will finally look like 0.8 sine of, let's say, 3100 t into 10 raised to the power minus 3 volts. This is the equation of the final answer. Then we have the next question as the Doppler effect, or the space physics question. Question number 8 says this is a spectrum that we can see increasing frequency, so the lambda is decreasing. So over here we will have violet, right? And this would be the red side. Figuring this out before solving the question helps you later decipher the question easier. This is the galaxy is moving away from the Earth at a speed of this. Okay, fine. Explain how the position of the line spectrum is seen by an observer on the Earth. What would happen to them if the observer or if the galaxy is moving away? We know this from Doppler effect that the red lines or the shift or the lines actually shift towards the red side of the spectrum or towards the longer wavelengths. If this side has shorter wavelengths, this side will have longer wavelengths. So we have to write this down in terms of English, right? So what do we write down? So galaxies moving away causes spectrum lines to undergo redshift. You get 1 mark for this. On figure 8.1, refer to the figure 8.1, they would appear shifted to the left towards longer wavelengths. So these lines will appear at this location, a bit shifted to the left or towards the red side of the spectrum. Okay. All right. So we mentioned due to the Doppler effect as well. So we get 2 marks for this, right? He says draw these lines or draw the location of these possible lines. So this is where the locations are. This is where the lines are going to be. This is going to be over here, and over here. Then we have 8.1 corresponds to electron transition to the level of negative 3.40 electron volts. One of the line represents 488, which will be closer to this side. This will be probably 488. Okay. Calculate the energy of the photon in this radiation. So no problem. We have E equals to HF. The energy is 6.63 Planck's constant raised to power minus 34. F we don't know, but we know the wavelength. So this will be 3 into 10 raised to power 8 divided by 488 into 10 raised to power minus 9. We get this F is equal to V divided by lambda from V equals to F lambda. And we understand that since we're dealing with light that will be moving at the speed of light, that is how we get this. So this is going to come out as 4.075 into 10 raised to power minus 19 joules. We can convert this into electron volts as well, no problem. So 4.1 into 10 raised to power minus 19 joules. Next part says determine the energy in electron volts of the energy level from which the electron transitions originates to cause the emission of this radiation. He says, where did the electron come from to come to this level and release 488 nanometers of wavelength? Where is the electron originating from? Where has it started its journey from? So first let's convert this into electron volts. So dividing this with 1.6 into 10 raised to power minus 19 gives me an answer of 2.55 electron volts. All right. So the very beginning or the very start is actually 0 electron volts. And as you move down, let's say this is your level EX and this is your level 3.4 electron volts, negative 3.4. So he says that what photon or what is being released. So the change in energy would be equal to the energy at X minus the energy at base, which is E naught, right? So this change is 2.55 equals to, this is the energy level X minus 3.40. So the EX level or the energy at this point comes out as negative 0.85 electron volts, right? So the photon that we have seen or that we are observing actually came from this energy level or this transition. It came from this point, fell down to this point, and led to the release of 488. Okay, so this level is negative 0.85, and as we go below, this will become more and more negative because removing the electron from that position, being closer to the nucleus, calls for a greater amount of energy that is required. So this will come out as negative 0.85 electron volts. Okay. Next part is determine the wavelengths in nanometers of the radiation detected by the observer at Earth. So of course the Doppler effect or the Doppler shift is expected from us. So the change in wavelength divided by original wavelength is approximately equal to the change in velocity divided, sorry, not the change in velocity, but velocity itself, velocity divided by c. So taking the lambda over there, this is the change in lambda is approximately equal to 6.2 into 10 raised to power 6 divided by 3 into 10 raised to power 8 speed of light multiplied by 488 nanometers. No need to convert the nanometers because we already are going to get the answer in nanometers. So the change in lambda comes out as 10.08 nanometers. Now, since we know that it is moving away, this change will actually call for a greater or the longer wavelengths, because as we can go back to the diagram, if this is 488, they will be shifted towards a larger value. So I will add this change into this answer. So the actual wavelength observed will be 488 plus 10.08. So the lambda observed becomes 498 nanometers. So this will be 498. So on the Earth, you will observe 498. But if you get closer to the galaxy, if you can catch up to the galaxy and see what that wavelength actually is, that would have been 488. That is what Doppler actually told us or taught us. So then he says Hubble's constant. So we need to use Hubble's law. V naught equals to H naught D. So velocity is 6.2 into 10 raised to power 6 equals to Hubble's constant is given in the data booklet, which is 2.3 into 10 to the minus 18, and then d naught. So the distance of this galaxy from us is 2.69 into 10 to the power 24 meters, which is very far away. So this is 2.7 into 10 to the power 24 meters. So 2.7 into 10 to the power 24 meters. You can convert this in light years as well. That's your choice. Question number 9 says, what is meant by binding energy? So binding energy is the energy required to break apart a nucleus, to break the nucleus apart in terms of its protons and neutrons and take them so far away from each other that fusion cannot occur again. That's why you see that in definition he says that they are now at an infinite distance. Why does he have to say the infinite distance? Because he wants you to understand that there is no chance of fusion any longer or anymore. Okay. So the next part is from mass defect question and topic. So he says mass defect, no problem. So when the nucleus is together, right, its mass is smaller. When it is separated, its mass is higher because you spend energy to break it apart, and that energy transfers or converts into mass. So let's figure out how many protons. So this protons, there are 84 protons, and 212 minus 84 calls for 128. So neutrons are multiplied by 128. So their individual masses will be multiplied by this. So let's write down that equation properly. So the mass defect will be equal to 84 multiplied by 1.007276, please use full values, plus 128 into 1.008665 minus, when they were together, 211.942749. Take all the values because the atomic mass unit is 1.66 into 10 raised to the power minus 27. So every decimal place counts because this itself is a very small number. So when you calculate this, this comes out as 1.7777555 U multiplied by 1.66 into 10 raised to the power minus 27 kg to convert U into kilograms, atomic mass unit to kilograms. So this becomes 2.95 into 10 raised to the power minus 27 kgs. So 2.95 into 10 raised to the power minus 27 kgs. He says find the binding energy. No problem, we will use the equation E equals to delta mc square. Use the mass defect 2.95 into 10 raised to the power minus 27 into 3 into 10 raised to the power 8 whole square. Don't forget the square. This is what students generally forget about. So this comes out as 2.66 into 10 raised to the power minus 10 joule. This becomes 2.7 into 10 raised to the power minus 10. Right? Then we have an easy question, binding energy per nucleon. No problem. This is the total energy required to break it apart. So 2.7 into 10 raised to the power minus 10 joules needed to break apart a nucleus that has how many number of protons and neutrons? It has 212 protons and neutrons. So 212 constituents shared the energy to break apart. So this will become 1.25 into 10 raised to the power minus 12 joules per nucleon. So 1.25 into 10 raised to the power minus 12. And then he says draw the graph up to 250. You're supposed to memorize this graph. So graph starts from this, then there is a bend over here and then goes like this. You can draw it more accurately like this. And we understand that at the peak there should be iron. So again, there is a problem over here. If you look at the complete dimensions, then this point at the center should be 125, half of 250. And somewhere along this line should be 50 or 56 or some half of this number, 75, let's say. It should be 75. You can take the measurements and then solve the question, right? So 56 will be somewhere along this line, the iron, which is the most stable. And then the graph goes down like this. And then he asks you to draw or show X, the approximate position of polonium-212. So polonium-212 will be somewhere along this line. Okay, so we draw X at this location. What I would recommend is use a ruler, measure the length, and then divide it using centimeters and millimeters. Then you can get even closer to the answer, even closer to 212. Okay, he says polonium-212 is radioactive, undergoes alpha decay. Okay, so let's write down that equation. So that is polonium-212 with the 84 breaks down to become something X by releasing alpha, which is 42, releasing some energy. So this is 208 and this will become 80. So this is more stable and this is less stable. That's why it underwent the radioactive decay. So he says, suggest and explain with reference to figure 9.1 why alpha decay of polonium-212 results in the release of energy. You see, the particles who exist on the right side of iron want to undergo fission reaction. They want to break apart because it's difficult to hold them together. And the particles on the left side of iron want to undergo or prefer to undergo fusion. Again, they want to become iron because iron has the highest stability, highest binding energy per nucleon. So just like in chemistry, you have gases or elements trying to match the noble gas structure. Over here in nuclear physics, elements are undergoing fission or fusion to match or to become iron, right? Okay. So as the nuclear number decreases, the binding energy per nucleon increases, so which increases the stability. This is what we've discussed over here, right? Question number 10, he says, describe the reflected sound pulse and may be used to obtain diagnostic information. He says, how do you use ultrasound for diagnostic information? So the reflected intensity that comes back from the boundary actually gives you the nature of the tissue beyond the boundary. What's beyond that boundary? What's beyond that tissue? And the time delay, how long it took to come back, actually tells you about the information of the depth of the tissue. How far away is it from the skin or from the outside? Then we have defined specific acoustic impedance of the medium, which is the product of speed of ultrasound in that medium with the density of that medium. And if you have the writing space available, you can write down the formula as well and mention the unit, which is kg meters per second. Then we have the system. He says there is a boundary between water and glass. He says determine the intensity reflection coefficient for the ultrasound, which is very simple as IR divided by I naught. This is the intensity reflection coefficient, and the formula is Z1 minus Z2 divided by Z1 plus Z2 whole square. You will sometimes find this formula as individually squared like this. Like this. That is also the same thing. But how do you find out the acoustic impedance? So you have to multiply these values together because these are the densities and the velocities, right? So after multiplication for water, the answer comes out as 1.46 into 10 raised to power 6, and this comes out as 11.4 into 10 raised to power 6 for glass. Yeah, I'm ignoring the 10 power 6 in this formula because it does not matter. It will be in the numerator and denominator will cancel out, so it does not affect the final answer. So this is 11.4 minus 1.4. 42. This is 42. This is 42. And divided by 11.4 plus 1.42 with whole square. So this comes out as 0.606, which is 0.61. What does this mean? It means that if I had a boundary over here and there was a tissue over here, there was a tissue over there, and in terms of, let's say, water and glass, so this is water and this is glass. So what has happened? We've introduced 100% the intensity of ultrasound. It bounced back on this boundary with a percentage of 61%. So 61% is reflected back. This is what this reflection coefficient or reflection ratio shows you, that in terms of this I naught, what we introduced, how much did you get back? We're getting 61% back. And how much will be transmitted? The transmitted intensity will be, of course, 100 minus 61, which will be now 39%. Okay, although this is not a part of the question, but explaining this in terms of when the question is about transmitted intensity. So over here, we're going to write down that coefficient as 0.61.